Alright, in this video, right, we are just gonna focus on this term known as oxidation state to help us understand how do we calculate this. Now, the oxidation state, right, its definition actually refers to the charge an atom would have if it existed as an ion. Not every substance will be an ion. For instance, if you take a look at H2O, say for example, are there ions inside H2O? No, right? Because you learn it as a covalent substance, right? So there shouldn't be any ions. Okay, so this is non-matter hydrogen. This is not a matter, right? So this is actually covalent. But it still has oxidation state because we're focusing on this word if. So for instance, if oxygen is an ion in this case, what will be the charge? If hydrogen is ion in this case, what should be the charge, right? So this is the meaning of oxidation state. Now, there's really a few rules that you must keep in mind, and it will take a bit of practice to get this in the right manner. Okay, so the first one, as we are looking at the elements, right, the oxidation state is always 0. What do I mean by that? Chlorine, this is just chlorine element, Cl2. The oxidation state of chlorine is 0. Copper is just a metal, right, which is a type of element, and the oxidation state will be 0. Carbon, 0. Helium, 0. Now, what do we mean by that? For instance, if you want to take a look at the oxidation state for oxygen, it's actually equivalent to 0. Why do I say 0? Because O2 is an element. So the first rule tells you that if you are looking at an element by itself, the oxidation state will always be 0. So that's what the first rule is trying to say. Second rule, if you are looking at a simple ion, okay, the oxidation state is actually the charge on the ion. Now, there's a bit of changes in the way you represent it, but basically you can take a look at the charge. For instance, you look at this thing called Cl minus, right? The charge, when you write it out, you write as 1 minus, right? Cu2 plus you write as 2 plus, and iron 3 plus you write as 3 plus, correct? The counterpart, which is their oxidation state, that means if these things are in ions, right? In this case, really ion, chloride ion, copper 2 plus ion, Fe3 plus ion, right? So the oxidation state, we actually write it by this, minus 1, plus 2, and plus 3. Do you notice something weird? Right, I think most of you have seen and noticed that, how come now this charge actually moves to the front when you talk about oxidation state? Now, this is always a way to represent oxidation state. Okay, this is the standard way of representing oxidation state. Okay, I'll just write OS for oxidation state. This is the standard way to represent. That means the symbol, right, the charge, whether it's positive or negative, should come in front, followed by a number. This is very, very different from how you write the charge. Because the charge you see over here, you always write the number first, followed by the sign. Number first, followed by a symbol. But for oxidation state, it's a bit special. So, you might want to take note of this rule number 2 itself, right? Because it's quite different from how you usually find out about the charge of the ion. Okay, let's take a look at the rule number 3. Okay, in rule 3, right, it tells you that, if the oxidation state of some elements, they actually have a fixed oxidation state. So what's the meaning of fixed? Basically, it tells you that there's actually a shortcut to tell once you're looking at them in a compound. For instance, hydrogen, right, in most compounds, the oxidation state is actually written as +1. Oxygen is given as -2. All group 1 elements are given as +1. All group 2 elements are given as +2. Let's take a while to think about why is this the case. For instance, right, if you look at HCl. So for instance, in this compound HCl, because there's a hydrogen, right, and because of rule 3, most of the hydrogen in the compounds are always +1. This hydrogen itself will have an oxidation state of +1, the oxidation state for the hydrogen. Now this is a rule that tells you that, most hydrogen inside the compound will be +1. Likewise, if you take a look at, say, CO2, okay, each of the oxygen will have a oxidation state of -2. Okay, so for oxygen in most compound is -2. Hydrogen in most compound is +1. Now for group 1 and group 2, actually it's pretty straightforward because group 1 elements, right, if they form a compound, they will form a 1+ charged ion. Remember, group 1 they form 1+ charged ion, so naturally their oxidation state will be +1. Okay, and group 2 they will form actually 2+ charged ion. Alright, so that's for the 3 rules so far. Okay, there's 2 more rules. Okay, the last 2 rules, right, are actually very similar. So basically, right, if you have a lot of elements inside a compound, right, like for instance CO, right, there's 2 different elements, carbon, copper, as well as oxygen, right, you realize that it has no charge. What do I mean by no charge? It means that there is no charge over here. Then what we have charge? For instance, if we take a look at rule 5, right? We realize that these are what I call so-called charges, right? You see the charges outside the polyatomic ions, right? When there's a minus charge, 2 minus, or whatsoever. When you look at rule 4, right, all these compounds, right, there's no charge. What does it mean? When there's no charge, right, it means that when you add up the sum of the oxidation states, right, of all the elements inside will be equivalent to 0. Now, what do I mean by that? If you look at copper 2 oxide, there's an oxygen inside, right? So if you try to recall in rule 3, it tells you that oxygen in most compounds has a charge oxidation state of -2. So the oxidation state of oxygen is equivalent to -2. Now, because there's no charge, right, it tells you that this oxidation state must be balanced by the other oxidation state, which allows you to conclude that the oxidation state of copper is actually +2, because with a +2 and a -2, you end up with 0, right? So, likewise, if you take a look at another example, say the Fe2O3, okay, same thing, there's no charge, right? Do you still recall the oxidation state of each oxygen? What's the oxidation state? Yes, according to this rule, it's actually -2. Okay, now when you want to conclude about the iron, right, something you must be careful of is that there's actually 3 oxygens inside. So, okay, maybe I'll just erase some of these other words over here. Okay, say because you have 3 oxygen, right, so the 3 oxygen will give you a total of -6. But when you talk about oxidation state, we're looking at one of the oxygen only, which is -2. So if the 3 oxygen is total is -6, right, and overall there's no charge, that means you can tell that the 2Fe must be able to balance out the charge, right? Which means that they must give you a +6. That means each of the Fe should be a +3. Can you follow so far? So the oxidation state of iron in this case will be +3. Okay, because you need to balance out the charge. Let's take a look at one more example. Say water, H2O. Same thing, there's no charge. Okay, likewise for nitrogen dioxide. But remember that in the rule, oxidation state of a single oxygen, it should be -2 in a compound. Right, this is the third time we're using this rule, right? And of course, in the rule, you also realize that oxidation state of hydrogen is actually equivalent to +1 in most compounds, right? How do you know this is the case for sure? So, same thing, I'm just going to erase this part away. If you take a look at this, one oxygen in water, there's only one oxygen, right? Actually gives you an oxidation state of -2, right? You have to balance up the entire thing to give you 0. There's actually 2 hydrogen that's inside, which means that these 2 hydrogen must give you the other +2, which in turn allows you to conclude that each hydrogen should be a +1, right? And it's in line with the rules that we talked about just now. Alright, can you try out number 4 by yourself? Okay, the nitrogen dioxide by yourself. Okay, and if you need to pause before the answer is being shown in 5 seconds, you may wish to pause now. If not, let's take a look at the answers. Right, do you get the answers correct? Right, so remember that the first steps to understanding about how to use the oxidation state is really for you to just go and try out. Okay, so if you make mistakes, at least you know what are the problems. Okay, some of you will make careless mistakes here and then, but it's okay, not to worry. Now let's take a look at the last rule, which is rule 5. Rule 5 is pretty similar. It says that if there's a charge, right, now the sum must be equivalent to the charge. It works in a pretty similar way. So, for instance, in this case, let's take a look at the oxygen first, or hydroxide ion, right? So, oxidation state of oxygen. Now, this is a compound, so the oxidation state of the oxygen will be -2. But you want the overall to have a negative charge. Am I right? Because O is minus, so it means that the oxidation state of your H, which according to rule 3 is also still only +1. Now, what's the significance of this? This tells you that if overall hydrogen is a +1, oxygen is a -2, overall you end up with a -1, right? Which helps to explain why the OH ion actually has a minus charge outside, which means that this -1 is expected and there's nothing wrong about that. Same thing if you take a look at, say, nitrate. The oxidation state of each oxygen, which is what the question wants, is always -2 in a compound. And I want to think of what will be the oxidation state of the nitrogen. So, there's 3 oxygen, right? So if each oxygen is a -2, oxidation state 3 will give you a total of -6. This -6 plus whatever is the oxidation state of nitrogen definitely give you -1 because of the minus charge that you see over here. If you do a bit of manipulation, you realize that actually the oxidation state of the nitrogen, right, is actually equivalent to -1 plus 6, which will give you a total of +5. Right, so with that, you can conclude that the oxidation state of your nitrogen is actually +5. So this comes with a bit of practice before you can get the hang of it. So can you try out number 2 and number 3 by yourself first? So you may wish to pause the video right now. So the answer, oxidation state of oxygen is always in a compound, most of the time, -2. Likewise for this sulfate one. In terms of the carbonate, the oxidation state of the carbon, in this case, due to the charge of -2 outside, right, overall there must be a 2-. So the carbon is actually a +4. In this case of sulfate, the sulfur will actually have an oxidation state of +6. Okay, so I hope you have gotten this correct. If not, we can always go through this when we're back in class. Now, moving on to the next page. It's also good to know that actually some elements, right, they actually have what we call variable oxidation state. What is a variable oxidation state? Actually, you have seen this a lot of times before already. You have noticed that, how come sometimes there's a 1, bracket 1, or bracket 2, or bracket 3 in the Roman numerals? For instance, iron 2. Right, then why is it sometimes called iron 3? Why is there a potassium manganate 7, so and so forth? Now, what this bracket actually tells you, right, is actually it tells you the charge, right? So inside iron 2 sulfate, you know that the iron is this kind of ion, iron 2 plus. Right, inside iron 3 chloride is actually iron 3 plus. And inside potassium manganate 7, it tells you that the manganese is actually having the oxidation state of 7 plus. Alright, so all these things actually tells you that what is the charge. So with that, if you translate to oxidation state, you should know that the oxidation state, like what I mentioned just now, right, when it's a type of ion, if you look at root 2, right, if it's a type of ion, right, the oxidation state is actually the same as the charge, just that you swap the symbol and the numbers. Right, so moving back to the page that we're talking about, if you know that iron 2 sulfate has iron 2 plus, then that means the iron inside actually has an oxidation state of +2. In iron 3 chloride, it will be +3. In potassium manganate 7, it will be, sorry, this is a plus sign, okay, it will be actually +7. Right, so this actually helps you to tell, without even doing all the formula, all the minusing, whatsoever, you actually can tell what is the charge, or in this case, what is the oxidation state of the substance. Do take note that there's a typo here. The formula is actually K, capital M, small letter N, okay, capital O, and number 4. This should be the formula for potassium manganate 7. Right, so now we're going to take some time to try out the practice questions over here. Okay, likewise, I'm just going to give you some time to try out the question now. So if you need, you can actually pause the video right now. So here goes. The answers for the oxidation state are as follows. For A is +2, followed by B +3, so on and so forth. So you can take a look at the answers. Feel free to pause the video as I scroll through the answers so you can take a look at what exactly is the mistake that you made. Do take note that in the oxidation state, the symbol should always be at the front, followed by the number. It's different from charge. Now, of course, know that if it's an element only, like in the case of example G, right, if it's just an element, right, there's no need for you to go and work out what's the oxidation state. You always just be 0, provided that it is an element only, okay, provided it's just an element. So just a recap, these are the 5 rules. Yep, so just a recap, these are the 5 rules, starting from rule 1, elements having an oxidation state of 0, if it's just a pure element, all the way to rule 5, where you need to take into account the charge, if it's a polyatomic ion, for instance. Alright, so I know that's a lot of work, and you do need more practice, so what's going to happen is that when you come back to school, right, there will actually be additional worksheet.